We chose our fan design based on in-depth research and adherence to the judging rubric. First, we chose a horizontal axis turbine because we found that these generate more energy and are more efficient than vertical axis turbines.
We chose to cut our blades from a Pringles can to creatively take advantage of the natural curvature of the container. We concluded that the curvature of the can would make for good blades, as it would catch more of the wind. The curve of the blade, due to the shape of the Pringles can, creates a curved airfoil blade to produce better performance and higher rotation speeds. We also chose to use a Pringles can because it is lightweight but also sturdy and would not need reinforcements, which would only make the blades heavier. The lighter the turbine, the faster it is able to spin, producing more energy. The Pringles can is also aerodynamic because it is very smooth, allowing for better and faster airflow. Our blades do not include any additional decoration in order to keep our design smooth and light. Adding aesthetics would take away from the efficiency of the design, and we find that the silver luster surface shows the good quality of our blades.
We also carefully designed the shape of the blades to ensure maximum lift. Our blade is flat at the bottom and curved at the top. This causes the air to move faster over the top of the blade because it has to travel more distance over the curved top. Meanwhile, the air moves slower under the bottom, flat part of the blade. This creates an area of lower pressure above the blade and creates lift to help move the blades upward.
We made the blade length the same as the width of the fan. We made the blades this long so that they would catch most of the wind from the fan, but did not make them longer than the fan because the longer the blade, the heavier it becomes. The blades were thicker in the middle because that is where the strongest wind hits.
We also carefully thought out the number of blades to use. The more blades that are used, the more wind the turbine catches, and the more efficient it is. However, increasing the number of blades also increases the amount of turbulent air, slowing the blades down. There is a trade-off between these two things, and we experimentally found that 6 blades was the optimum number of blades for our design. Having less than 6 blades did not catch enough air, and more than 6 blades produced too much turbulent air and slowed our blades down.
We chose to attach the 6 blades to 4-inch long wooden dowel rods with hot glue because the glue is relatively lightweight and would keep the blades at the right angle. We need a sturdy connection because if the blades move or the angle of attack changes because of the wind blowing back on it, the energy we create will decrease. We connected the blades to our given hub by screwing the dowels in tightly.
Another important component of our blades was the angle of attack that we used to secure them to the hub. Making the angle of the curve too steep didn't catch enough air, and making them too flat did not propel the blades fast enough. Therefore, we angled the curve about in the middle of these two extremes, checking that this was the optimum angle for our design experimentally.
To produce the maximum of power with our turbine design, we used the biggest gear we were provided. This is because there are more teeth on the big gear, so it turns the small gear more times per rotation of the turbine. All of these aspects are combined to create the best turbine possible.